Chapter 11 focuses on Cantor and his great theorem of the challenge of the infinite. Before we can actually approach and analyze Cantor's great theorem, we have to look at mathematics through the centuries that led up to his great theorem. In the 18th century, it was considered the century of Euler because Euler had really no rival to challenge him, and all of his theories and his great theorems were kind of the overall arching ideas of this 18th century. Now, in the 19th century, there was no single preeminent mathematician. Okay, unlike the century of Euler, there really wasn't a single mathematician in this era. But there were some common themes in the 19th century. There was deeper analysis of mathematical foundations from Euler, Newton, and Lisbon from previous years or centuries. And mathematics during this time kind of drifted away from the applicable constraints from the real world to what was considered non-Euclidean geometry. And it was considered non-Euclidean because it didn't really follow Euclid's elements that we've previously studied. In this non-Euclidean world, similar triangles actually became congruent, and there were no longer just 180 degrees in a triangle. So that was kind of strange for that time, but there was really no logical contradiction to this non-Euclidean world or this non-Euclidean geometry. So it really didn't make sense, yet there was no way to kind of disprove it or contradict it. Along came the 18th century, and math continued to carry so far from the real world that it was not even recognizable to physicists and engineers. The book actually goes on to say that math was transformed into little more than a pointless exercise in chasing tiny symbols across a page. Now, another very vocal critic during this time frame was Maurice Klein. He was a mathematics historian, and he also agreed that math ventured too far from its actual roots from the early Greeks and even Euclid himself. But there was some rebuttal, I guess, from mathematicians saying that these mathematical theories that were coming about, no matter how abstract they were, had very surprising applications to real-world phenomena. So the craziness of this non-Euclidean geometry was actually used and kind of showed up in physics and astronomy. So another battle actually going on during this time period, besides this illogical or craziness of non-Euclidean geometry and how math was kind of venturing from its roots, was actually the foundation of calculus. From Newton and Lisbon, we've seen how these two have really influenced calculus, or even both of them co-fathered the course or the idea of calculus. But the foundation of calculus was very fuzzy, because the whole idea of calculus, or at least its foundation, relies on the idea of a limit. So there was fuzzy language with the infinitely large or small quantities that were used to describe the limits around the birth of calculus. Now, Newton used his fluxions that we've kind of seen so far, and his idea of a fluxion was what was trying to find the ratio of two quantities and then determine kind of what happened to these ratios as they both moved towards zero. So this was kind of his idea of a limit because he used the word limit to describe the ratios of these quantities. And he even went on to identify what was, or at least what he considered the ultimate limit, was how these terms, I guess, vanished, but it wasn't that they were vanishing before or after. They kind of reached this zero moment, but at which they actually vanished. So his definition of this ultimate limit was kind of fuzzy because we can understand the idea of these ratios before they vanish, where they actually have a quantity or a value, so that idea was okay. But he went on to say how they would vanish, or we had to analyze these quantities after they vanished. Well, and that kind of left a question mark, because how can we analyze or understand something after it's gone? So it's kind of fuzzy going on in his definition here, but we can also consider the precise instance at which they vanished being the ratio of 0 over 0, but we know this has no meaning, okay? It's undefined, we can't divide by 0, so his idea of a limit was considered an illogical definition because of the wording he specifically used. Now, Lisbon, on the other hand, he phrased, I guess, his idea of a limit as infinitely small quantities. So he's getting away from this idea of vanishing or kind of reaching this 0 point. He used infinitely small quantities. So he said that it's not 0, but you cannot be decreased any further. And what was kind of illogical about this is because the word he actually used. Okay, he said infinitely, which actually means it can be decreased further by definition, infinitely small. So again, another illogical definition of a limit, because he's saying it's not 0, but you can't decrease it any further. But the word infinitely kind of means that you can keep going, I guess, in an infinite fashion. Alright, so moving on from Newton and Leibniz, I guess I mispronounced his name earlier. Okay, crazy name. I always had trouble pronouncing it, but it's Leibniz. We move into two more people that kind of were dealing with this idea of a limit and its illogical definitions from the foundation of calculus. The first person is Augustin Louis Cauchy. Okay, he's Frenchman right over here. And he said that a limit can be described when the values successfully attributed to a particular variable approach indefinitely a fixed value so as to end by differing from it by as little as one wishes. The latter is called the limit of all the others. Okay, now talk about wordy. But notice how his definition of a limit doesn't really involve the same wording or vocabulary that Newton and Leibniz used in theirs. Okay, he has no infinitely small, there's no infinitely large. We're not talking about that precise instance the variable reaches the limit. And this is what mathematicians call the limit avoidance definition, because we're trying to avoid these particular, I guess, words in the definition. And Cauchy used this definition to prove major theorems in calculus. And with this specific word right here in his definition, approach, kind of rose the ideas of motion in terms of the calculus field. Now, indefinitely in his definition was too, I guess, indefinite and vague. And mathematicians, even though they liked his definition, just like we kind of look at it ourselves, it is entirely too wordy for us to kind of understand or use. So even though he used it to prove some major theorems in calculus, it's just a little too wordy for people, I guess. So in comes Karl, and excuse my butcheredness of his last name, but Weierstrass, I guess, comes in this German, and he is accredited to creating the arithmetization of the calculus definition. And this is what I actually hated in my calculus course. Okay, it was the bane of my existence. We normally call it today the delta epsilon definition of calculus. So thank you, Mr. Karl, for ruining my first week or so of calculus. But he came up with this less wordy definition. It's entirely mathematical, totally symbolic, and it's not vague, and it's mathematically solid and still used today. So this is his definition of a limit. Please don't ask me to go over it, because I think to this day I really don't understand the whole idea of what this is saying. Don't get me wrong, I know what a limit is, I know how it works, I know what it looks like, but this to me is just kind of a foreign language. Alright, so now that we kind of understand what has been going on previously to Cantor's great theorem, we're going to take a look at why he actually had to challenge the idea of this infinite, in kind of other words, challenging the idea of a limit, I guess, in a sense, is that infinite motion. So as mathematicians kind of focused on this new epsilon delta definition from Karl, they kind of, instead of those vague ones, they made some particular unsettling discoveries about rational and irrational numbers. Now, just as a refresher, rational numbers, or in other words, the ratio of numbers, are fractions, and they can either have terminating or repeating decimals. Irrationals cannot be expressed as fractions, and they have no repetitive pattern and proceed endlessly. So I guess for some examples of irrational numbers, we could have the square root of 2, even the value of pi, and rationals, just basically anything that can be turned into a fraction. So what was going on with Cantor in this challenge of an infinite that we're leading up to is they kind of, these mathematicians were looking at rationals and irrationals on a number line, and they kind of noticed how they are densely distributed, meaning that between any two rationals there lie infinitely many rationals, and kind of on the other hand, between any two irrationals there lie infinitely many rationals. So the conclusion based on these two ideas, or these two realizations, is that real numbers, okay, kind of the union, I guess, of rationals and irrationals, are evenly divided between rationals and irrationals. So the amount of rationals and irrationals are roughly equivalent. Half of the real numbers would be rationals and the other half would be irrationals. But in the 19th century, there were some discoveries that proved this not true. Okay, there was actually a function found, okay, a function existed that is continuous at each irrational number, but discontinuous at each rational number. But there was no function that existed in the other direction. So there was no function that existed continuous at each rational and discontinuous at each irrational. So this kind of discovery of this particular function that was continuous at each irrational and discontinuous at each rational showed how there was no symmetry or balance between the rational set and the irrational set. So that kind of led how irrationals and rationals are not interchangeable like mathematicians had previously thought they would be, and this kind of confused them. So Cauchy and Weierstrass and colleagues placed the foundation of calculus on the limit, just like we've kind of been talking about, but mathematicians were starting to realize that some of the most important fundamental questions of calculus rested upon the ideas and properties of sets. Okay, these irrationals and rational sets were somehow tied to this idea of a limit. And now this comes in to where George Ferdinand Ludwig Philip Cantor comes into our story. He's considered the creator of set theory, and I think he should win the best prize for the best name ever. Alright, so now we're just going to talk about kind of the man behind the math and revisit Cantor and how he progressed through mathematics. He was born in Russia in 1845, and he actually moved to Germany when he was 12 with his family. He came from a very religious and musically, artistically talented family, and he earned his doctorate from the University of Berlin actually under Weierstrass. And the research he did during his doctorate and his time in school led him to sets and the importance of comparing sizes of sets, meaning he kind of looked at counting in a different sense, and this plays a huge role in our great theorem. So he said that two sets M and N are equivalent if it is possible to put them in such a relation to one another that to every element of each one of them corresponds to one and only one element of the other. Now in modern mathematics, this definition or this idea of his is in a sense what we consider cardinality. If they both have the same size, they're considered cardinal to each other, I guess you could say. So they have the same cardinality if they meet this definition. But notice how there was no requirement on M and N to be either a finite or an infinite set. Now, up to that point, I guess sets were looked at in a finite sense, but this infinite set was kind of uncharted territory. Now, predecessors to Cantor believed in what was called a potential infinite, meaning you never ever run out of whole numbers, whereas Cantor kind of approached it from a different level. He considered what was called a completed infinite, where it was a completed entity. Okay, a set is actually complete to be compared with other infinite sets. So even though whole numbers or rational numbers or irrational numbers could be or are considered an infinite set, he believed that they are actually a completed entity. There is actually some end, and this we're actually going to see this idea of a completed infinite show up in his great theorem. So when he went through his great theorem that we're about to get to, he had two fundamental premises. One of them was that the cardinality of sets, okay, the size of the sets, had to be determined by matching, okay, kind of showing this one-to-one correspondence. And he had to use his idea of a completed infinite as a valid concept. So there's actually some truth in this idea of being completed and never ever running out like his predecessors believed previously. So he kind of confronted the idea of the infinite face to face, and we're about to see how it was unprecedented in how he actually did this. Alright, so here is Cantor's first proof in his challenge of the infinite. This is not his great theorem, this is just something he uses in his great theorem, so we're going to kind of go over it because it's pretty important. He let n be the set of the natural numbers, and e be the set of even natural numbers. So notice how they are completed sets because we're actually showing how there is some type of end to them. Even though they are considered an infinite set, okay, there are infinitely many natural numbers, there are infinitely many even natural numbers, we're showing how there is a completed end somewhere in these sets. So that they are completed sets in spite of actually being an infinite or infinite in nature. And they have the same cardinality, they have the same size of each other since we can put them in a one-to-one correspondence. We can match the number 1 from the natural numbers to the number 2 in the even natural numbers. We can match the number 2 in the natural numbers to the number 4 in the even natural numbers, and so on and so forth, even in a general sense in this fashion, and so on and so forth forever. So we say that n matches one and only one number to e, and e matches one and only one number to n, so they have the same cardinality. They're actually the same size, but this was very, very paradoxical since, I mean, we kind of imagine that there should be but half as many even numbers as whole numbers. So it's kind of a weird idea to think that all of our natural numbers have the same size as the even natural numbers. So in this case, we either have to reject the notion of a completed set by arguing that we can't consider the natural numbers as a self-contained entity, or we have to reject the simple definition of equal cardinality, being able to put things in a one-to-one matching correspondence. But if we accept both, then there are no fewer even numbers than natural numbers, which is pretty crazy for us to think of. Now, in a similar fashion, we can actually compare the set of integers, okay, a negative and positive whole numbers as well as 0, and the natural numbers again. And z and n have the same cardinality based on this matching of one-to-one correspondence. Again, we can match a 1 from the natural numbers to 0 in the integers. We can match 2 in the natural numbers to 1 in the integers, and so on and so forth, kind of alternating through the positive and negative whole number in this integer set. So what we say is that any set which could be put into a one-to-one correspondence with n, meaning how it is, it has the same cardinality, is considered to be denumerable. Or this is a pretty big vocabulary word, especially for when we get to the great theorem, but it's considered denumerable, or it's countably infinite in a sense. And what Cantor did was he kind of developed his own special number or representation, I guess, of this denumerable idea. He called it a transitive cardinality number. It's actually pronounced elif naught. Okay, I think I said that right. And he uses this notation here to represent the number of items in a denumerable set, meaning that it's the cardinality of the natural numbers. So just a little example here of how we can kind of use a set as a reference point. In this case, we can say a set will be said to have 5 elements if its members can be put into a one-to-one correspondence with the fingers on our right hand. So this is a very ambiguous way of determining when a set has 5 elements. Okay, our fingers are kind of used as that standard reference point. So if we can match items to each of our fingers on our right hand, then the two sets would have the same cardinality. They would have the same size. So just like how we're using the fingers as a standard reference point, Cantor used n, okay, the natural numbers, as a reference point or a benchmark to extend the number system beyond the finite. Because remember, he's kind of challenging this infinite. We're extending it beyond the finite. And n was the prototypical set having this denumerable elements that we talked about before. Now, some also that kind of comes up is this notation of m with a little bar over it, meaning a cardinality of the set. And we already saw in our conclusion previously that our natural number size, okay, the cardinality of our natural numbers is equal to the cardinality of the even natural numbers because we can put them in a one-to-one correspondence. We can match them up precisely with each other. But we were also able to match up the integers with the natural numbers as well. So notice how they have the same cardinality. Okay, they're all these sets, at least their sizes, are equal to each other. So all of these sets would be considered to have that LF naught notation. They are all denumerable. They all have the same cardinality of these natural numbers. But Cantor kind of wanted to extend this idea to rational numbers. What about the set Q? He said that they're densely distributed, so they kind of differ from integers because integers are uniformly one unit from each other, such as 1, 2, 3, 4. And he believed that rationals are actually more plentiful than naturals, or natural numbers, since they are infinitely many, meaning there are infinitely many rationals between any two integers. So Cantor said that rationals are actually denumerable. Okay, they have the same set, they have the same cardinality as our natural numbers, and he did this by specifically showing another one-to-one correspondence. So in order to show this one-to-one correspondence, or in other words, how Q is denumerable to n, is by Cantor set up an array to help him do this, kind of a picture to help him. So he developed this array of rational numbers starting with 0, and he moved in this diagonal fashion through his array. So he starts with 0 and moves to 1, then he goes to 1/2, over to -1, over to -2, down to -1/2, down to 1/3, down to 1/4, down to a -1/3. But notice how he skips 2/2, which is essentially 1 that we already counted. So he's going through all these rational numbers, all these fractions, but he's skipping fractions that have previously appeared. So when you take this movement through our rational numbers and put them into correspondence with our natural numbers, we have this one-to-one correspondence between our natural numbers and our rational numbers. So since there's a one-to-one correspondence, we are able to conclude that there are as many rational numbers as natural numbers, meaning the rationals are denumerable. They have the same cardinality, the set has the same size as our natural numbers. Now up to this point we've kind of shown how a lot of different sets are denumerable, like they have the same cardinality, the same set size as our natural numbers. We showed the even natural numbers, we showed the integers, we showed the rationals, so it may seem that every infinite set was denumerable. It had the same cardinality as our natural numbers, but actually in 1874 Cantor wrote a paper called On a Property of the Collection of All Algebraic Numbers, where he actually found a set that was not denumerably infinite, meaning it did not have the same cardinality of our natural numbers. And this particular set was the real numbers. Okay, so there was no interval of real numbers, regardless of how small its length or its size, that could be put into a one-to-one correspondence with n. And this is actually what our great theorem actually kind of involves or entails. Okay, so his initial proof about this denumerability of the real numbers required some advanced math tools, but we're going to kind of use a simple proof as we go over the great theorem. Alright, so let's dive into the great theorem, the non-denumerability of the continuum. Now, non-denumerability in this case just means that it has a different cardinality than n, okay, so it's not countably infinite. And the continuum, at least in this case, is the interval of real numbers from a to b, where x is in between a and b. So if we were to think of a continuum, kind of a number line, where we're dealing with an a value and a b value, we're specifically looking at x values in between them. So we're going to kind of show how we're beginning and ending in between b. And in this particular great theorem, he used the interval of 0 to 1 in this proof. Now, real numbers in this interval can be expressed as infinite decimals. Notice how we can represent 1/2 as 0.5000 repeating, 3 11s, we can have that 0.7 repeating, and even pi over 4. Okay, even though it's not a repeating decimal, it is an infinite decimal found inside this interval. So for this particular proof, we need to assume kind of something very important, that 1/2, we're going to represent it as 0.50 repeating instead of 0.99999 repeating, so that the decimal representation of any real number is unique. Okay, we're not going to have these two pieces showing up that mean the same thing. We're going to make sure that each decimal representation is unique. And in order to prove this great theorem, Cantor used a reductio ad absurdum argument, very much how Archimedes did, which is essentially a proof by contradiction. Now, since we're approaching this by a proof of contradiction, we're going to assume that our conclusion is true, but kind of show how something crazy happens at the end. So we're going to first start off our proof by assuming that the natural numbers in our interval from 0 to 1 can be matched in a 1-to-1 fashion, meaning that our interval from 0 to 1 is, in fact, denumerable. Okay, it has the same cardinality as our natural numbers. So suppose a correspondence can be set up in this following fashion over here, where we can match any number in our natural numbers specifically to an x value found within this interval with some unique decimal representation. So even in a general sense, we can still make some type of 1-to-1 correspondence. Now, if this were really a 1-to-1 correspondence, then every real number inside of our interval 0 to 1 would appear somewhere over here on the right-hand side, and it's specifically matched with a particular natural number on the left. But this is where the craziness happens. So now we're going to suppose that there is a real number b with some unique decimal representation, but we're specifically going to pick our decimals in a specific fashion where b sub 1 is any digit different from the first decimal of x1 in our previous list, but again, not 0 or 9, so we have that unique decimal representation. Now, b sub 2 is going to be any digit different from the second decimal of x sub 2, but again, not 0 or 9. Same with b sub 3, any digit different from the third decimal of x, or of our x sub 3 in our real number set over here, but not 0 or 9. And b sub n is going to be any digit different from the nth decimal of x sub n, but again, not 0 or 9. So we're specifically picking these decimals in a particular fashion. So just as an example, our first decimal of x sub 1 was 3, okay, right there. So b sub 1 can be any number different than 3, and it can't be 0 and it can't be 9, so let's just say it's 4. Now, b sub 2, the second decimal of x sub 2 was 0. Okay, somewhere right there. So let's just say b sub 2 is 1. Okay, it can't be 0, it can't be 9, so we're just going to pick a value of 1. The third decimal of x sub 3 was the number 2. So again, we can't be 2, we can't be 0, we can't be 9, so let's just pick a value of 3. The fourth decimal of x sub 4 is 8. And again, we can't be 8, we can't be 0, we can't be 9, so let's just pick 7. So our real number b that we're specifically picking in this fashion would start to look like this. So this leads us to two simple but actually contradictory facts. So the first item we can actually realize from this is that b is a real number since it is an infinite decimal. Okay, we can keep picking decimal places till we're blue in the face. It is an infinite decimal. But b is actually not equal to 0 because we were never able to actually pick 0 as a decimal in its kind of continuum here. But b can also not equal 9 since we were not able to, or sorry, b cannot be 1 since we were not able to pick 9. So b strictly falls between our overall interval of our real numbers 0 and 1. So then that must mean that it appears somewhere over here on the right-hand side of our list, since it is a real number, infinite decimal, that falls in between 0 and 1. But the other fact is that b cannot appear anywhere actually among these x1, x2, x3 values, since b is not equal to x sub 1 because their first decimal place differs. Okay, we specifically chose it to be different. B cannot equal x sub 2 because their second decimal place differs, just like we had to pick something different. And b is not going to equal x sub n because their nth decimal place differs as well. So while our first item here tells us that b must be on this right-hand side, the second item tells us that it cannot be here since it has been designed explicitly not to match any of these real x values. So even though the first part tells us it should be here, the second item is telling us it should not be here. So by contradiction, our assumption that a one-to-one correspondence between these natural numbers and our real number interval exists is false, and so the set of all real numbers between 0 and 1 is non-denumerable. So now that we know that the set of real numbers specifically between 0 and 1 is non-denumerable, there were some implications of this proof, and actually the infinite set of rationals was denumerable as we kind of shown previously, but the infinite set of real numbers between 0 and 1 was actually somehow more infinite, okay, based on his proof, since Cantor found a number that does not correspond to n. Okay, we were actually able to find that number b that did not correspond to these natural numbers. So points in this small interval from 0 to 1 are so abundant that they outnumber the positive integers. Okay, so this little set is actually somehow larger, even though it doesn't have the same cardinality, okay, it's not denumerable, it's somehow larger than the positive integers, which is kind of crazy to think about. But there was also this idea of extending the idea of an infinite to irrationals instead of just looking at rationals and real numbers, which kind of led to a larger difference between rationals and irrationals than them just having these different decimal properties of repeating or terminating decimal places. So in comes a theorem U, or in other words, union. And this theorem states that if B and C are denumerable sets, and A is the set of all elements belonging to either B or to C or both, then A itself is denumerable. So in other words, A is the union of B and C, so A equals B and C together, or the union of both. So looking at our proof here, it's the assumed denumerability of B and C kind of guarantees that the individual one-to-one correspondence exists, meaning we can take our natural numbers and somehow correspond each of those natural numbers to an item or a set value or element in B, and we can do the same thing over here for C. So this assumed denumerability means that we can actually put B and C into a one-to-one correspondence with N. But what we can actually do is jump between these elements of B and C to generate a one-to-one correspondence between N and A, which is the union of B and C. So we can take our natural number 1 and correspond it to our first element in B. We can take our natural number 2 and correspond it to our first element in C. And we can take our natural number 3 and correspond it to the second element in B, and so on and so forth. So if we're including in this case all of our elements from B and C, that was our kind of definition of A, because A was the union of both sets. So since A can be put into a one-to-one correspondence with our natural numbers, A itself is denumerable, and consequently the union of two denumerable sets is always going to be denumerable as well. I guess you can think about it in this sense, if you're Italian and you marry an Italian, then your children will be Italian. So if your first set is denumerable and your second set is denumerable, then the union of both of them will be denumerable as well. So what Cantor had to do was use this idea of the sets and the union being denumerable to help him determine the denumerability of the irrational numbers. And so we're going to take a look at, really quickly here, the difference between the rationals versus the irrationals in terms of their denumerability. Now, we already know that the rationals are denumerable from previously, and we use the letter Q to denote the set of rationals. But we're kind of trying to figure out here, what about the irrationals? Are they denumerable? Are they non-denumerable? What's going on here? Now, I use the letter C just for irrationals because if you're irrational, I guess you're kind of crazy, so that's why I'm using the letter C to kind of illustrate this point here. So what's going on here is that we're going to take a look at our rational numbers and the union of the irrationals. Now, we already know that the rationals are denumerable, and we're kind of questioning ourselves here, what about the irrationals? Are they denumerable as well? So if we assume that the irrationals are denumerable, then the union of these two sets should be denumerable as well by this theorem U. But here's what's kind of the kicker here. Notice how the union of the rationals and the irrationals is the set of real numbers. And since we know Q, okay, the rationals are denumerable, but our great theorem proved that the real numbers, the set of real numbers, is non-denumerable, that means that our irrational numbers must be non-denumerable as well. Because if the set of irrational numbers was denumerable, then the union of these two denumerable sets must be denumerable as well. So by kind of merging our great theorem and this theorem U, we ultimately find that irrationals are non-denumerable and far outnumber rationals. Okay, they are far more infinite than the rational numbers. So what Cantor kind of did in this proof, or in his research, I guess you could say, is he challenged this idea of an infinite, and it's kind of crazy because all these strange theorems and findings about these sets and rational and irrational numbers kind of arose out of the desire to just probe into the deeper secrets of calculus and the idea of a limit.